Hi, everybody. Welcome to the Earth Engine and Deep Learning Part 2 Dynamic World session at Geo for Good. I'm really excited today to welcome Oliver Guinan, who is an engine manager at Google, Valerie Pasquarella, who's from Boston University, Fred Stolle, deputy director from our forest program at the World Resources Institute. And today we're going to talk about a novel new data set that some of you may have heard about before from previous Geo for Goods called Dynamic World. Today we have some really exciting updates to share on Dynamic World. First, we have a refresher on our goals for this project, which are to apply what Google does like no one else, bring massive compute and modern artificial intelligence to produce a novel land cover data set and make this data and the models and the training data open and free for everyone. Ultimately, we believe land cover data is critical for many stakeholders, and we're most excited about countries who are looking to reduce carbon emissions from land use change, help them meet their goals recently announced at COP26 to reduce and stop tropical deforestation, and also help companies meet their goals around zero net deforestation and sustainable supply chains. So you know about Matt Hansen's seminal work using Earth Engine for global forest change, and that unlocked so much, but we didn't have a clear picture of what's outside the forests, like grasslands and croplands and urban areas, which are the major drivers to deforestation and also emitters of carbon into the atmosphere. We wanted a high-resolution, globally consistent data set, and with the release of ESA's Sentinel-2 catalog, we got right to work. And we set out to build Dynamic World, and World Resources Institute developed the taxonomy for our land cover classes, and National Geographic Society built a training data set comprised of dense markup over 24,000 Sentinel-2 scenes. And here's just a quick preview of what we've got. Next slide. We see a lot of promise in deep learning techniques like this model, which produces a map showing a snowstorm in Boston in February for advancing the field of remote sensing. And we're still at the beginning of the application of AI to remote sensing, but we're excited to collaborate with research institutions to leverage the Earth Engine platform for dynamic geospatial analyses to inform action by policy and decision makers. Imagine if you can have all kinds of data about land, about carbon, about biodiversity, instead of a map taking years to produce. You run a model over thousands of machines and suddenly you can see what's happening on the landscape within seconds. And everyone can access this data and create derivative data products. So now I'm going to hand it over to Ollie to talk to you a little bit more about what's under the hood.
Thanks, Tanya. Hi, I'm Oliver Guinan, and I'm an engineering manager on the Earth Engine team. Going from reflectance data in Sentinel-2 images to a rich description of the world across 9 classes was a major technical challenge. I'll talk through the process of creating the data set at a high level, given that the paper is currently in journal review. First, we designed a process to account for cloud cover. We focused on scenes with less than 35% cloud cover based on the Sentinel-2 metadata. We then ran the S2 cloudless algorithm on each individual scene. We removed pixels between the cloud and any potential shadow based on the sun angle, leaving us with the most usable pixels for further analysis. We then created a novel machine learning model to encode the training data. We did try common deep learning approaches like UNet and DeepLab, but found that they didn't effectively encode the detail available across the Sentinel-2 bands. We created a training process to account for some of the uncertainties and quality issues in the training data itself. The paper goes into more detail, but it was important to account for the fact that the training data had some uncertainty and that the real world at 10 meters is far more complex than it is at 100 meters. So we took our model and we applied it to every Sentinel-2 top of atmosphere scene. And this means that every 2 to 5 days, we have current global coverage. Since we're taking Sentinel-2 less than 35% cloud-free scenes and running the dynamic world model over those scenes as they're ingested into Earth Engine. We also ran the model on every scene going back to the beginning of the Sentinel-2 archive. That's June 23rd, 2015. And together, this creates a data set in the Earth Engine catalog that unlocks all of the value that's in the Sentinel-2 data set. So with every pixel characterized across 9 classes, we can empower users to move from analyzing reflectance to analyzing dynamic world output for a large number of tasks. The output catalog parallels the Sentinel-2 image collection with the same scene IDs, allowing users to move seamlessly between the two collections. Although some pixel values might not be very logical, bright areas like salt flats can appear as snow and ice, but because that class best represents the brightness of the land in our taxonomy. Those values are still useful since they characterize the land really effectively at 10-meter detail. Using the probability scores across the 9 bands allows users to go deeper, training classifiers and building reducers to characterize the land beyond the tier 1 classes. And Earth Engine is, as we know, a great platform to do exactly this kind of analysis. So in summary, Dynamic World is not just another discrete land use land cover product. The primary use case is supporting really detailed land use analysis on top of these 9 probability bands, giving you a supercharged version of analysis-ready data. So now I'm going to hand over to Valerie, who's going to go into a lot more detail on the time series.
Hi, I'm Valerie Pasquarella, and I am research faculty at Boston University and just starting as a visiting researcher with the machine learning data products team here at Google. And so today I am going to go a bit deeper, as Ollie said, into the time domain of the dynamic world image collection, specifically 3 major innovations that have come with dynamic world. As both Ollie and Tanya mentioned, we've got this near real-time image classification where we're getting land cover predictions for each new Sentinel acquisition, as well as the whole back archive of top of atmosphere images. This is leading to all sorts of exciting things in terms of time series analysis. And in addition to the traditional top 1 or winner takes all label that you see in a lot of land cover products, Dynamic World also has bands for individual class probabilities. And finally, we're able to take this image collection of classification results and derive all sorts of interesting map products. So there's a lot of customization opportunities and using all those standard Earth Engine tools, reducers, classifiers in order to build on top of or condense the dynamic world collection. And so we've seen some animations of dynamic world. Here's an example where we're looking at the real-time, the single date predictions and the underlying Sentinel-2 image that they're based on. This is a reservoir in central Massachusetts, and you can really clearly see that shift from the ice and snow covered winter time period through leaf on and kind of growing season greenness with the forest and open water. Next. And shifting this from the spatial to the temporal domain, we can drill down into that one little white point. And here we see a chart of the class probabilities for that 1 10-meter pixel. And again, that transition, this one's in the reservoir, from ice and snow into water is super clear. We can also see the model's really confident in these results. So we've got a high class probability for snow in the winter and water in the growing season. And those class probabilities come into play in other ways we look at dynamic world data. So again, you might be used to seeing maps where you just look at a single top 1 label. And yes, you can do that for dynamic world, but we've often added this hillshade visualization that takes the confidence in that top 1 class and adds a shadowing effect. So where you would normally see this kind of flat forest and water landscape, we start to see details like the power line corridor that cuts through the forest, as well as that transition from the forest and water edge, where the model's not so confident in that top label. And so seeing this uncertainty really adds a lot of context to the way we're interpreting results. The other big innovation, again, is that ability to create your own map products. So Dynamic World is an image collection. It is not truly a map unto itself, although we have these predictions for individual dates. We really hope that users will be able to take those predictions and start to derive from them all sorts of interesting composites for different time periods and different areas. And here we can see a side-by-side of a top mode composite for the beginning of 2021, so January through May. The middle, we've got May through October, and then the end panel is the full year of data. And you can see when we get a lot of snow and ice and more patches of cropland and grass herbaceous areas in the early season. We get much more confident and kind of closed canopy forest in the growing season. And then all of those uncertainties kind of coming together in the full year prediction. So just one of many sets of examples that you could derive from the 2021 results. And so after seeing all these cool demos and hearing about Dynamic World in the past, I'm sure people are chomping at the bit and ready to explore. And so today I am really pleased to introduce a new tool that we've been developing to help people start to explore the Dynamic World collection. We've got a Dynamic World app that has all of the functionality that I just showcased. So this app allows you to display a top one mode mosaic with the hill shading at higher zoom levels. It kind of disappears at further zoom, so you can get that real global scope of the data set, but it adjusts automatically. You can click the map in order to display one of these probability charts for the different cover type predictions. And really great, you can click the chart in order to load the single date prediction and the underlying Sentinel-2 image for that date. And so using the layers list, you can then slide the transparencies and really inspect both the single date predictions, their source imagery, and you can adjust the dates and reload the charts and map results to really hone in on the composites you'd like to see, as well as all of the observations that are contributing to them. And you can access the app at our homepage, sites.google.com/view/dynamic world, hyperlink there on the slide. And in closing, I'd like to share an example of not just how we can use Dynamic World for looking at things within year changes. So we've seen ice and snow and these other state transitions that might not get reflected in the more standard annual land cover products. This slide, I think, really highlights the power of Dynamic World in going all the way back through the Sentinel-2 top of atmosphere collection, going back to 2015. And we've got a clear cut out in Oregon and really seeing the model track that high probability of forest until the forest is cut, at which point it becomes a less confident mix of grass and shrub and scrub. We see some of those winter transitions with snow and ice coming through, but really lots of opportunities to think about how you could use Dynamic World for both across year and within year tracking of landscape dynamics. So in closing, I just want to summarize a bunch of points that have already been made in working with the Dynamic World predictions. First, Dynamic World is a model that is proxying human annotations and Sentinel-2 reflectance properties. So we're combining supervised and unsupervised methods, and what you're getting is the most spatially refined predictions of these labels based on both those annotations and the source imagery. Second, we've got some mist clouds and shadows. As Ollie pointed out, we've got a really robust cloud masking procedure that incorporates different data sets and algorithms, but there's still times where we don't catch all of the clouds and the shadows, at which point you'll see some misclassifications, often clouds and shadows as snow and ice and water. And, you know, hopefully being able to look at the time series and the source imagery will help you isolate those misclassifications and avoid any unexpected results because of them. Third, we've got those class probabilities to help you characterize uncertainty. So you're not just getting a single label, you're getting the full suite of information to help you understand the predictions and how confident the model was in the labels that it's assigning. Fourth, we are able to create custom composites for any specific date ranges. So again, Dynamic World is a almost innumerable number of different maps hiding in this image collection, and we leave it to users to start to use Earth Engine reducers to group those observations, to transform them into products that represent periods that you're interested in, whether that be seasons, years, months, all possibilities there. And finally, as Ollie pointed out, there's this really unique opportunity to take the Dynamic World collection and build on top of it. So take those class probabilities, combine them with your own training data sets, with other ancillary data, and use them as inputs to classifiers to refine and develop new maps as a result. And with that, I am going to turn it over to Fred to introduce some Dynamic World applications for forests.
Thank you, Valerie. And my name is Fred Stolle. I'm from the World Resource Institutes. I want to go a little bit further on the importance of this data set for ecosystems and forests. And, you know, a paraphrase here, something that apparently Napoleon said, there's a quality in quantity. And I want to make that a statement of there's a quality in resolution. For if you want to think about biodiversity, carbon, and ecosystem services, this is incredibly important. And you see here a picture, you know, of a satellite data, which is 8 kilometers by 8 kilometers. The previous NOAA generation was this. And you see, if you look at this data, you know, and it's a combination of forest and open forest, you know, this might be, you know, 170 million ton of carbon in this forest. But now, if you go in a better resolution, we're talking about 1 kilometer region, you see so there's so much more detail coming in here. And that also means like it's not all forest, it's not all open forest, there's some grassland, maybe some croplands in. And if you would think about how much carbon is there, it's a bit lower because there's more grassland than cropland in. When I go even better in my resolution, I'm now 500 meter or modest resolution here, we come suddenly now much more detailed. We actually can see maybe there's a band of forest and there's a band of grasslands, but there's also lower carbon estimation. And now I go into the resolution of 100 meter and you see again a very different picture. And I'm not going further to the 10 meter, but I think you get the idea. Resolution really, you understand the impact on the ecosystem so much better. And so you see how far off you were on the 8 kilometer data. So that is very important in this data set, that resolution matters. And what we just talked about, you know, in this all the previous example, you see we're talking about a 10 meter global data set, temporal, very defined. You know, that means there's so much more interest here. And here you see again 100 meter resolution data, very good data. But if you think about what a 10 meter data gives you, you see suddenly there's so much more detail. If you see in these areas, you didn't see that before in the data, but now you see all kind of extra data here that is happening in this intact forest, that maybe this intact forest is not so intact. I zoom in this area, in this lake here, and you see here the 100 meter and the 10 meter data, and you see maybe unfortunately that this intact forest is not so intact. And I zoom even further in because we have the possibility even now with this 10 meter data. And actually see that this intact forest is not so intact. There's actually crops, there are some settlements, there's some roads. And when I look at the even further and I put the satellite data here, you see there is a lot of activity in cropland here. There's crops, there's a road, there's other things happening. These are data we couldn't see before. For our ecosystem values understanding, this is so much important to see that this forest is not intact. There's all kind of other things happening. And, you know, this really improves our understanding of the earth, you know, because data is explicit, you know, data is spatially explicit. Things happen for a reason somewhere and not somewhere else. Here you see a satellite image, you know, and maybe so this is classification of the data from dynamic world. Maybe it doesn't tell you so much what it is, but I hope in this next slide you'll see that this is Washington, D.C. You see the National Mall, and you see how good this data captures just, you know, the simple data that we have here, where there's green, where there's cities. It again increases our understanding so much more to have this high resolution data, where we can do so much more understanding our ecosystems of the world. With that, I want to give it back to Tanya.
So there you have it, dynamic world. We're really excited to see what you're able to do with the data. And thanks again to the European Space Agency for making the Sentinel-2 catalog publicly accessible and available for us to build novel data sets like Dynamic World on top of. Many thanks to Ollie, to Valerie, and to Fred. And happy coding. Hi, everyone. My name is Tanya, and I'd like to welcome you to our live Q&A. I'm here with Ollie, Valerie, and Fred, who you just heard from. So over the past hour or so, you've been asking some really great questions that we're excited to answer. It's not too late. You can still submit your questions below the live player in this video. So we're going to go to our first question. It's for Ollie from Emile C. Great presentations. Looking forward to hearing from the team about when dynamic world data will be available to the public.
Yeah, thank you for that question. Glad that you're excited about it. We're sharing the data with the Gear for Good community through Earth Engine as a partner preview. You can get access to that data today. You can see the links on the right side of the screen that will connect you with some tutorials and give you examples of where to get to that data set. We will have more to share in the future, including a public entry in the data catalog for Dynamic World. We'll share the training data that was used to train the model, created in partnership with National Geographic. And that will come with the release of a publication in a journal, which is currently under review, as I mentioned in the talk. So yeah, we hope you enjoy the data, enjoy the tutorials, and a shout out to Ujjwal Gandhi for helping us to put those tutorials together. Back to you, Tanya.
Thanks, Ollie. So the next question is from Valerie for Job DV. Why would you limit your scene selection for Dynamic World to images with less than 35% cloud cover if you apply a cloud masking algorithm anyway?
So the reason for this is twofold. First cut, it makes it easier to reduce the massive amount of data that we're processing out of the Sentinel-2 archive. So by using the metadata attribute, we're filtering down to the clearest scenes that are giving us the best spatial coverage. And the flip of that is when we have the clouds being masked, we're also using the directional distance transform approach. There's a bit in the S2 Cloudless page on how to use that, but we remove the shadows as well. And when you remove both the clouds and the shadows, what's really left over at the kind of 35% cutoff is not much. And so what we're giving you in the collection is the clearest images with the most spatial coverage and reducing the fractional amounts that you're seeing there.
Great, thanks, Valerie. So our next question is for Fred from Elliot. He says, this is awesome. Can you speak to how Dynamic World compares to the Microsoft AI for Earth land cover mapping and prediction product? I think it's now called Pearl. So Fred, over to you.
Thanks. I didn't know it was called Pearl, but it is indeed good to be a remote sensor, I think, at this moment. We have some great new products. I also wanted to shout out to the European Space Agency with the world cover data, also 10-meter global data, static data, and of course the Microsoft Pearl, as it's called now, Esri data, also 10-meter, both as static data, as far as I know now. I think they're still working on a paper, so we can get more. But so it's good new data. They're still coming out with a paper, so we'll look into it, how that will be different, and that will be one of the exciting things, I think, in this coming months and year to figure out what are the differences and what can see one. Just to say that our data set's a little bit different here on Dynamic World because we look inside the year. So you get inside the year, you get actually data, and that the land cover is just a function of all the data layers. It's a big data cube where the land cover and probability are in. I think that's one of the new things in this Dynamic World data set that, as far as I understood from the Esri, hasn't come out yet.
Thanks, Fred. We have another question from Emile C. For Ollie. Since you indicated using the full Sentinel-2 archive for the Dynamic World product, are you then using the L1C top of atmosphere reflectance data instead of the L2A bottom of atmosphere reflectance data, since the L1C archive is longer?
Yeah, thanks for that question. It's an important piece of the model and the modeling approach was using the top of atmosphere data. So we can go all the way back to 2015, the start of the Sentinel-2 archive, for historic data. Obviously you're getting more usable pixels if you look at surface reflectance, but that data, the time period was shorter. So we put some more smarts into the model to deal with top of atmosphere data.
Great. And the next one is for Fred from the Royal Society of Protection of Birds, RSPB. Really interesting to see these linear features picked up by the top one hillshade. Are there any plans to use this information to map like power lines or tracks?
Yeah, it is. It is really interesting how Dynamic World sees those linear features, and I think we are very happy with that. Now, are we going to go further on that? Yes, we think, but I think this data set is especially for users to do interesting things with it. And I think from the Birch Society, we would love to see how we can work together, because I hadn't thought about that use as, oh yeah, indeed, lines, important for bird migration. It's a good idea. We haven't thought about it yet, but would love to start thinking with you how we could use this data better.
Awesome. Thanks for the question. That's a good question. For this one is for Valerie or Ollie from Ethan K. Amazing. Do you use any post-classification smoothing filters?
I guess I can take this one. The model is context aware, so it's a convolutional neural net. It has a lot of spatial smoothing in the map domain, but in terms of temporal smoothing, no, we're looking at single image predictions at inference time. And so what you're getting is a prediction based on that snapshot. But applying some sort of post-classification filtering would be really interesting. Next approach, I believe the Modus land cover collection has some Markov chain modeling in there to prevent like unnecessary flipping between classes. So all sorts of potential for applying temporal smoothing to clean up some of those class transitions.
And this next question, Valerie, is also for you, or it could be from Ollie too, from Cheryl Q. Do any of these data sets capture canopy roughness to help distinguish between a plantation and a more structurally complex forest? This is the $1 million question. Good one.
I can take a first crack at this a little, but actually Valerie should probably take this one. She is the forest expert.
So the training data set includes all sorts of different examples of trees, and really it's a trees class, not a proper forest class. If you're going to get rougher structures, you would definitely see some differences in the per pixel probabilities, but really, yeah, it's a trees class, and I'm going to say I haven't looked at a ton of plantations, but I don't think that the surface roughness is necessarily going to show up quite so obviously.
Yeah, one thing I'd add is that in plantations we do sometimes see more bare ground between trees, because we they have that structure to them that they tend to be planted in straight lines. So we don't have that sort of typical forest floor coverage, and you'll see tree be the most common class, but you'll see bare ground be more common than it is in a natural forest, for example. There are interesting subtleties like that are deep in the data that we think are the kind of thing that makes building classifiers here really an interesting direction to go.
Great. Thanks so much. I think that's all the time that we have, time that we have for questions today. Again, we want to emphasize this is an active area of research. There is still room for improvement. We're really excited about the progress that we've made so far. And this is why we're releasing it to the community. We're looking for folks to build upon it. And so, that's also our fundamental open data principle behind this data set. So tell us what you think on the Earth Engine developers group. We'll be watching that space. And check out the resources section under the live player for some tutorials to get started with the data. So thanks everyone in the audience and on our panel for joining us today. And also big thanks to Chris Brown, who is responsible for the bulk of the work that we presented today, as well as our partners at WRI and National Geographic Society. Thank you.